No, here they are, baby. Our favorite section, right? So this is electrical potential. Electrical potential, that's going to be in volts or joules per coulomb, right? This is our charge. Strangely, it's a positive Q, just like they use for heat. I'm fine with that, but it just seems kind of odd. And then this is the distance we are from it. Remember that if you're away from a positive charge, your potentials are positive. If you're a distance from a negative charge, your potentials are negative. It's just a negative number in there, right? Okay. This is gravitational potential. Right? The negative means that all gravitational potentials are negative, okay? Really, if I've got, some object here and some object there, the energy I've got really is the reason why it's negative is that it would take work to pull them apart. To get them to zero, I'd have to put energy into this thing to get it to zero. Zero energy is these guys being infinitely far apart, okay? And this is interesting, right? Because the universe has so much matter, and the matter represents positive energy. But all the gravitational potential energy is negative, and so it's possible the universe has zero energy content, which is interesting. All right, and this is a mass, right? So this is some mass, and we are some distance from it, right? And that's the potential at that point, right? These guys relate the field to distance, right? This is the data packet's one stab at coherence, and they do a pretty good job here, okay? This states that that the work per unit charge or work per unit mass, okay, is just G times R. Or the potential change in potential is going to be G times R, like this, right? So this is gravitational field strength in newtons per kilogram, right? This is our potential. This is in joules per kilogram, and then this is our meters, distance moved, right? This is the same thing with electricity, right? So it's change in voltage over R. So if I've got a couple plates, we did this all the time, right? We got a couple plates like this, and we've got, let's say they're 3 meters apart is the distance they are apart. And if there's 1200 volts across them, right, the electric field is 1200 over 3 is 400 volts per meter. Right, so that's what this is. This is electric field is electric potential divided by distance, and then this is gravitational field as well, right? And by the way, if I plug this in, change in V is really its work divided by mass, right? The work is mgh divided by mass, right? And if I go do that, I get gh, right? And so all this formula says is that G is GH over H. It's like, yes, it is true. Okay, and then potential energy is also mass times voltage, right? Mass times the potential. Sorry, this is gravitational potential, right? And then if you substitute this in for gravitational potential, you get this, okay? And then this says that electric potential, so this is energy, right? Gravitational potential energy is mass times the gravitational potential, and then you substitute that in for the gravitational potential and you get this. You could have done that yourself, but they did it for you. And then here they're saying electric potential, right? This is actual energy, this is in joules, right? Is charge times electrical potential or voltage, right? And then that's kq over r. No, it's not r squared, right? And they got that by substituting this in for v, right? Okay, and then this is the force of gravity, right? This is the force of the Coulomb force, right? Where K is the ad hoc 1 over 4 pi epsilon naught, all wrapped together, the 8.99 times 10 to the minus, or 8.99 times 10 to the ninth, the positive ninth. Okay, this is our formula for the velocity of orbit. It comes from mv squared over r, the centripetal force, right, equaling G planet mass, satellite mass over r squared, right? Satellite mass cancels, right? The r goes away. V is the square root of gm over r. There it is. It's all solved for you. Presumably they won't give you period or something like that. I don't know. Okay. This is escape velocity. So this comes from what? 1/2. If it's got escape velocity, the kinetic energy is equal to the, whoops, I'm sorry. Let's do it the right way. So kinetic energy plus negative the potential and gravitational potential energy, right? Some plus a negative G m over r is 0. This adds up to 0. So remember, if it's got escape velocity, it can get infinitely far. You've got a planet, right? And you're escaping from some distance r, and you shoot this thing up in the air, right? It has escape velocity if it can get all the way to infinity before it stops, right? Okay, it's a complex thought there, right? It can get all the way to infinity before it stops. So basically what that means is its total energy is 0. This is its kinetic energy. This is its gravitational potential. That's got to be 0, right? So the m's cancel, right? And then I can multiply everything by 2, so I get v squared is 2 gm over r, and then I can square root stuff, and I get this thing, right? So this is our escape velocity, the minimum velocity to get to infinity. Yeah? How's that?